Okay, good afternoon. When I looked at the program yesterday, I was thinking, oh, that's a nice talk, that's a nice talk, that's a nice talk. Oh shit, this is my slot. Someone actually made the recommendation I should actually do something that you all run out of the room so you can see at least one of the other rooms. But fortunately, we have that videotaping, and at least theoretically, I will have the chance to catch up with the other talks. So this is a talk that I actually gave a couple of times already, but still, it's not only the talk that it's repeated, the stuff that I'm talking about is really old. But I learned from Kevin Henney at OOP in February, old is a new. And a lot of old stuff that I consider, oh, that was solved 20 years ago, happens to be not solved everywhere. And one of the issues that I observe from time to time is people are rediscovering stuff and reinventing stuff and still get it wrong, or slightly not like it should be used. And one question I have to the audience, I always ask the audience. My students hate me for asking them questions where they have to raise their hand. Even though they are Swiss, so they're used to vote every 2 months or so. So who is actually writing unit tests or test automation using a test framework? Who is not doing that? Okay, that's not too bad. Who is using a framework to mock other objects that are not existing? Who has written a mocking framework? Okay. There are a few situations where mocking frameworks are good. There are most situations where mocking is good, but there are plenty of situations where mocking frameworks can actually make your design worse. And that's what I'm talking about. Plus some other ranting arbitrary about stuff that's going on. So, you're still in the room? Good. For you, bad for me. I'm relying on work by others, and I want to point out, if you don't have these books, grab them. If you write tests, and if you write tests for code that already existing. The one is X-Unit Test Patterns by Gerard Mészáros in the Black-Red series from Martin with Pearson or Edison Wesley. And the other one is Working Effectively with Legacy Code by Michael Feathers. Anybody having these books already, at least one of them? Okay, about half of you. Thank you. And for Michael Feathers, legacy code is code that doesn't have tests. So at least we have one person in the room who has legacy code. Or maybe he's not programming, that's, I don't know. Another old fellow, Martin Fowler, he wrote an article about 11 years ago, mocks aren't stubs. And that's a little bit of terminology stuff. So when Gerard Mészáros calls replacement objects that you use in a test instead of the real thing, test doubles. And there are different categories of test doubles, and the terminology is not always clear, but there are stubs that replace an object and have a kind of a dummy default behavior so that your actually test code can compile and run, and mocks do something else. They actually do more, and what that more is a part of my talk, and stay tuned. And the interesting thing, in that article, Martin Fowler has a nice example, a whiskey store. And he's getting Talisker from a warehouse with an order, and for me that is a very interesting design, and I believe it's deliberately bad design. So the order has is let's say the interface that you're using and the thing that you want to test. And the warehouse has some interesting features like, okay, you can query if something is available and how many, or query for how many are available. You can insert something into the warehouse and remove something and even ask how many are there of a given thing. And instead of whiskeys, we have strings to represent these whiskeys. And an order has knows what and how many of something you want to get from the warehouse. And if you order something, the order queries the warehouse, dear warehouse, do you have enough whiskey? And then the warehouse says yes or no. And if there's enough whiskey, it's removed from the warehouse, the order is fulfilled. Otherwise, the order fails. And what we have is we have the order and another component the order depends on. And these other, if I want to test the order, I have to do something about that other dependent component or dependent other component. And the order is our system under test, what we actually want to test in that situation. And actually we want to test, okay, please fulfill the order. And then something happens within the order and it will return and I can query, are you okay or did something fail? So we have system under test, SUT, and dependent other component, that's the other thing that we don't have. This is what we want to test. This is some other dependency. And with all design that has dependencies, tests get ugly. So unit, if it's encapsulated, everything is there, easy to test. Unit with some other dependency, it's a tangle. And usually those dependencies get transitive, and that's where you get messy stuff. And you don't want to have messy test cases, because then you cannot judge if they are right or not. Trick question. What is the McCabe cyclomatic complexity of a typical unit test? Who knows about McCabe complexity? Okay. How many different word, how many branches do you have or paths through the test function do you have in a unit test? Good. Who is having test cases with more than, where the test sequence is more than one? If you would be my students, fail. So take that home. A unit test is just sequence. The only statement that you have is statement sequence, so semicolons, no ifs, no loops, nothing. That's a good unit test. So Gerard Mesaros has nice pictures and terminology. He claims we to have 4-phase tests, and that's there are others who say, okay, we have AAA tests, but the principle is the same. You set up something, you do something, and you check if it's okay what you did. And in some languages that don't have destructors like Java, you typically have to tear down what you build up in your setup phase so you don't leak and have clean stuff afterwards. And the setup and tear down are especially important if you have these dependent other components, because that means you have to do something about if that's something that's outside of the scope what you're doing, and that might be reused, like a database. You might need in tear down to reset the database to previous state. Otherwise, you end up with things where you either import the production database into a test environment or the other way around, which both happened in practice in my career. Not from me, but in the vicinity of where I was working. So the typical setup initializes a system under test, and because it has another dependent other component, it might need to have that component plugged into the system under test when it's created or set up. Then you do something with it. It might incorporate state changes and calling out to the other component. And in the end, you verify that what you expect from the system under test actually happened in a way that you wanted it. So like considering our warehouse, the order gets initialized, gets a warehouse component, and then you say, oh, please give me my Talisker whiskey because I'm so thirsty and I want to have a party. And then you check if you got it or not. And the thing that's here, cloudy here, that having that other component that system under test is dependent on, that's what's called a test fixture. So you have to set up this thing with some other component so it actually can work as it is intended to behave. Who has done that already? Okay. Questions? Now, when should I actually need these other components? When do I actually have to replace those other components? Because if I build a system or write a test for a system, that might just exist and I might can use the original, but sometimes I actually have to replace the original. Not always. That's something, a typical mistake that's made. Oh, I want to test the unit, I only test that unit, and all other dependent components that it depends on, like string, std string in C++ or std vector, I have to have a replacement because I want to test that thing that uses a string or a vector. Don't do that. When do I need? When the object that I'm using has a non-deterministic behavior and you have unpredictable results, the other component. What can I do about that? A test where I don't know if it succeeds or fails, that's a very bad test case. If you have tests that fail spuriously, bad thing. Especially if that's on a build server and it's cloudy or stormy all the time, nobody actually cares if there are any tests at all. Sometimes it might be very hard to set up, like, oh, I have a complicated other component, the whole subsystem, and creating that is really hard, so I want to replace it to be able to test something. Sometimes it has a very hard to trigger behavior. Oh, what happens if I want to write a file and my disk is full? With terabytes, having a disk full error is rare. Filling a terabyte to actually test what happens when the disk is full is also something not very practical. And so you have to do something about that, but sometimes you actually want to have that out-of-memory condition or a network error because you want to test your error code. And that's usually the code that is least tested and has the biggest problem when you get failures. Sometimes stuff is just slow. Like, oh, I have a robot that moves around. I want to test the robot control code. If the tests run as slow as the robot moves, it's very hard to figure out to find real problems in the code before you actually have to move the robot. And sometimes it's about user interfaces where I need to click there. How do you click from a test when you don't have a mouse or a mouse pointer? Or I expect the user to do something here, and now I have to react on that. How do you simulate the user? Write a test where a pop-up window, please confirm, or click here, or enter that here. That's not what you want to do. And sometimes, in very few cases, and that's blue because that's the case where you might want to actually have that mocking thing where you check if the usage of the dependent other component is done as intended. And that's when the other component has when you want to make sure that it's called correctly, so that you didn't make a mistake in calling that other dependent component. And a last situation where you have that is, oh, the real object is not there yet. You have a team, a distributed team, and those guys over there in the States, they do something interesting, and we have to use their code, but we don't have it yet. So we need to have a replacement, and that's where you have a fake what's there. Or, oh, we have such a big system, we have to start somewhere, but we know there's some other thing that we need to depend on, but that's not there yet. We have a design sketch, and we know that the other component needs to be there, but we want to start here because we don't know yet what goes in the other component. And that's a really dangerous thing if you actually use a mocking framework in that last situation. Because, as I will try to show you over the next hour, that's where you end up fixing design without an easy means to change it, or where the change is much harder later on. So the basic thing that Gerard tells us is, okay, if I have to verify the logic of this thing and it depends on some other component, I need to have the means, or I might need to have the means to replace that other component because it has one of these features on the list on the previous slide where it is slow or has some other problems. I need to have a replacement that is just giving me the right answer. And that's called a testable. And setting up the testable requires a fixture. And to get there, or let's first stop there. To get there, I will show you. So that's how I avoid slow tests and tests that might fail spuriously or whatever. Just, I want to replace that other component with a testable that behaves nicely, is quick and easy, and I know the result that's coming from it. And that's where I have a replacement for the other component. So I actually can test the logic of this component. And if I end up in that situation where I actually want to check that behavior, remember the blue bullet item, that's where we actually want to see if the system under test is calling out to the other component in a specific way so that I can, in the end, check if this other component was called in the correct way, with the correct parameters, maybe in the correct sequence of calls. And that is where mocking actually happens, where you have that replacement object, a mock object that actually memorizes how it is used, in what sequence the calls have been made, and in what arguments were given, and then allows you to inspect, was the calling sequence, were the arguments in a way like I expect this system under test to behave. Like, instead of, let's say you get something from the warehouse and you have to pay for it. Both things have to happen. Otherwise, one of the parties gets cheated, either the customer or the salesperson. That's something where you want to make sure that all things happen to have a complete transaction, as an example. So I can implement these mock objects by hand, or I can use a mock framework. And Gerard Meszaros has some interesting, tiny, fine print words in there, what he thinks about having these stuff configured instead of programmed. And that's my claim that he's right, but nobody reads the fine print. So what he's saying, okay, there are solutions where you actually have a configurable testable, where this thing, this replacement object, is not programmed, so you can program it, but it's kind of generated or provided for you by some magic. And that magic, instead of programming, you start out configuring it. And that's the idea that's overused in mocking frameworks. And there's a specific, in the fine print of Gerard's book, it says, okay, please be aware that this configuration can be more complicated than programming it in the first place. And also it couples this part with this part very closely. And why do we have that idea of these configurable test cases? When unit testing was first invented, actually people were writing these things by hand, and then someone came out, oh, this kind of repetitive code patterns, why don't we just use reflection in Java and magic to make this code happen? And one of the reasons it was done is when it was conceived, Mauch was one of the first ones. We had reflection in Java, but we didn't have lambdas or any similar way to provide small pieces of code to execute. Just returning a default value required you to create a class to plug it in and have that functionality somewhere. And the IDEs at that time were not that clever to generate just the implementation of an interface with default behavior for you. So that's the reason. We didn't have lambdas, we didn't have easy ways to program that stuff or even to generate it from somewhere. So the Mauch and some others as well at the same time frame, late 90s, created infrastructure so you could actually configure the behavior of this testable. Instead of programming it, you could configure it. You got a kind of a generic object where you say, oh, if that happens, please return that value. And that's the core idea of most of the mocking frameworks around. Oh, I can configure expectations and return values, and in the end, I verify that this happens. And these configurable test doubles can be interesting and good to use, but there's an inherent danger that this configuration gets more complicated than writing the method code in here first at all. And I know at least one of here, or some people are here who wrote mocking frameworks. Getting that stuff implemented is even more complicated. I'm sure Björn can tell you about that. So what's in the mocking framework or in the infrastructure for doing mocking? One thing that's a nice term, it's dependency injection. Who is using that term daily? Shame on you. It's just, okay, I program against an interface and use instead of a concrete object. That's all about dependency. Have parameters. That's dependency injection. Instead of a concrete dependency, have a parameter where you can replace something. It's nothing magic. It's just a magic word, dependency injection. I have been, let's say I'm an experienced patient, and injections are not what you want to have every day, even if it's just dependency. So the big thing is this other component that we had, we need to have the means to give that replacement, the test double there. And one means is actually what Michael Feathers called, we introduce a seam, where you can actually rip apart and glue something else in, or stitch something else in, and then use that something else, the test double, instead of the original part that was put there. So instead of using a kind of a welding torch to make that thing, we do something that we call dependency injection. So we provide parameters. And the nice thing some frameworks provide, okay, I can fake the other component with the test double. So just returning canned values, or yeah, that's actually what people call fake or stub. And then comes the interesting part. That's where actually the gluing happens. You can use tracing. Frameworks provide a tracing mechanism to trace the calls, how the other component was used by the system under test. So you actually have a temporal coupling of what happens between these two, and in the end you have to check if that was okay, And that's where matching or matching infrastructure comes into play, where you say, okay, I want to guarantee that the other component is used in exactly that way or in some kind of somehow like that. So this call first, this call second, this call third, or all of these calls have to be made and I don't care about the sequence, or this call first and then as many of the other calls as you like, just to make sure it's used correctly. And that is where the super glue comes in between the system under test and the other components and the interface there, because once you have that manifested in your tests by using the mocking framework, it's very hard to refactor, and we will see from examples why. So some frameworks that I showed you, there's GMock. Who's using GMock? Who's loving GMock? Still some love there. Who's using trompe-l'oeil? Ah, you have a user. And who happens to use develop and maybe have tried Mockator? None? Especially with Gmock and Gtest, just because something comes from Google doesn't bless it. Google has a software engineering problem. Any Google employee here? Okay. They have a software engineering problem. They have to hire very bright people who have a very bad software engineering education. And I know that from firsthand, and whenever you visit a Google office, you might still see the testing on the loo sheets in the bathrooms. They have a software engineering problem. And their C++ guidelines were rubbish when they were created, and they're still used in some places. Don't use them. The core guidelines have some issues, but fewer than the Google guidelines. Okay, let's get back to Michael Feathers, because I like his work, and he's a nice guy. And he has spoken here as well years ago. So what is a seam? A seam is actually something where you have that dependency, where that dependency injection happened, where you can change behavior without changing the code in that place. If you have an editor and recompile, you can change everything everywhere, but you want to change something without having to change it. And he defines 4 different kind of seams that are applicable to C++. One is the object seam. That's a classical approach that Java and many other object-oriented languages do. Okay, to be able to exchange something, you program against the interface instead of a concrete class, and so you can exchange the concrete class under the hood and provide a mechanism to make that change, usually in the constructor of an object to actually provide an argument with the concrete class. Or employ the strategy design pattern. Who has not used the strategy design pattern in his life or her life? Oh. Who has no idea what the strategy design pattern might be? Learn about it. That's old stuff, that's the new. So you pass the testable usually as a constructor argument by reference, so you can actually program against that interface and provide a different implementation for your specific test case of that interface. That comes in C++ with the overhead. You have virtual member functions, you have the indirection, and Louis Dion told us how to make it a little bit less expensive with a little bit more complicated code bases. And I'm not there yet, but his ideas were good yesterday. But in C++, we have another thing to get flexibility. And if we compile our test cases separate from the rest of the world, we can actually do something where that Michael Feathers calls a compile seam. And we have these template parameters. So instead of programming against a specific class, we provide a template parameter to the system under test and give that class as a default template argument to the template parameter. So we can substitute it for the test by compiling it with a different class, a different template argument, and have a replacement for that concrete dependency. No overhead in the production code, and very good control over what happens in the test code, especially with the object theme. You have to, if you have pure virtual member functions in the base, in the interface, you have to implement all of them in the derived class for all test cases, even if the tests only use a few of them. So with the template parameter, if the code called in the test only uses, let's say, 10% of the potential functions of the template class, of the template parameter, then you only need to implement these 10% because code that is not called is not instantiated in the template, so it's not happening, so you don't have to fulfill all of what potentially could happen. So that saves you coding time if you do it by hand. Michael Feathers provides two other means to introduce themes. One is using the linker. That is to actually be able to replace stuff that you might get from a standard library, like, oh, I want to read and write a file and want to check if my reading and writing is actually called correctly. How do I do that? And there are tricks that you can do, for example, with the GNU linker to get these replacement stuff, and I don't want to go into details here, because if you ever want to go there and want to do that by hand, it's tricky. You might employ our IDE, and it provides that for you, but it's rare. We actually cannot change existing code to replace these calls. And if it's a last resort, you can even use the preprocessor to replace stuff under the hood by just defining another name for a name that's called, which works quite okay for C functions, not so well for C++ functions where you have overloads, and if you only want to replace one overload, bad luck. Or if that name happens to be used somewhere else as well. This is a principle. If we have a system under test relying on a dependent other component, we extract the interface and implement a stub or a mock object implementing that interface, and the unit test will actually configure that system under component using that mock instead of the production code, which would use this dependent other component. That's the visual summary of what I just tried to explain. What does it mean introducing a theme? For our warehouse, let's get back to our bad example. We have this concrete dependency. Fortunately, it's only used in this fill from method. So we have this, our unit test. We extract the interface of the warehouse, still have our original warehouse. We have to adapt that to implements this interface or inherits from that base class in C++. And now we can actually have that mock warehouse that implements the same interface, and our test case will actually provide the order with that replacement. And we also need to have here the interface warehouse, which I forgot to put in this diagram. So as all my talks are advertisements for our IDE, we implemented that refactoring, introduce or extract the interface from an existing class, making the member functions virtual, providing a virtual destructor, and all member functions are pure virtuals. And if you do that, we have that original warehouse class. All this was with the blue bar here is automatically generated for you, and it's plain code, so you can adapt it, you can change it, you can refactor it, like changing interface and stuff like that, of a signature of a specific function. Doable, plain code, done. And that's regardless of which mocking framework you use. If you want to have that object theme infrastructure, you get it. Even for GoogleMock, you need to do that, and we do that for you. Compile theme is a little bit different. You have to extract template parameter. Also refactoring we implemented for Cvelop. I'm not sure if C-Line has something similar yet. Didn't check in the last year, but you can ask the JetBrains, nice JetBrains people over there if they have that. So if you then provide a mock warehouse class in your test case to give as a template argument. If you just write struct and curly braces, it wouldn't have the required member functions like it's called from the order class. The good thing is, well, you can actually generate the code for that by the IDE, so that if you have that mock warehouse and order, and for an empty warehouse, it would be okay that the order could not be filled, and that's what's done for you. So for the successful order, yeah?
You use assert. I've been told for many years that using asserts in tests is just a nightmare. Because assert, from what I understand, will crush the tests if the assertion is not true.
Well, that is a capital assert from our unit testing framework, ACCU2018. It's not C-asserts assert. C-assert asserts will actually stop your program by terminating, but this is not the lowercase assert, and it's rare to use just this macro assert. Usually you would, very often you might use assert m or some assert equals, where you actually compare stuff with an expected result. It's just because it's a Boolean, assert equals doesn't make much sense. So it's not the lowercase assert crashing your code. It's an assert that will tell you if your test failed and the remaining test case will continue to run. Did that answer your question?
Yeah, we're just using Qtest, and in Qtest...
sorry, I can't...
we use Qtest in the company, it's for the Qt, and the assert crashes the test. So this is why there was my confusion. But it's fully explained, thanks so much.
Well, are you using, when you say Qtest with the letter Q, or...
It's okay, for him that's a red flag, but it's okay to explain.
So this assert doesn't crash your test. It's not C-asserts assert, and it's from ACCU2018. That's the test framework that I wrote. But, yeah. I will show you more where mocking frameworks can crash tests in a minute. So that was the easy part with the empty warehouse where it just failed and the default return of a bool is false, so everything is fine. But now we want to have the successful test case. And how do we provide, okay, that has inventory Talisker will actually answer true, and the remove is actually called, and we want to check if that remove Talisker is actually called. So how do we test that intended usage of the warehouse? So we have to program something or do something about it. And there are different approaches what you can do. With the developer, you can actually generate the code for that empty warehouse or for another warehouse, and that's plain code, so you can actually do something here for your specific test case so it does what you want to. Done. Plain code, programming, that's what you can do. Easy, simple. If you do use a mocking framework like GMock or Trompe-l'oeil, well, things aren't that easy. Why? Well, they don't write plain code, both of them. They create infrastructure around you to simulate or to configure these mock warehouse objects to allow you later on providing in the test case expected behavior things and required behavior and then test for that it actually happened. And so you write your classes in a very specific ways using macros that magically generate code for you, and I hate macros. And Bjarne hates them as well, so it's not my own problem with macros. And especially what's even uglier, you have to have different macros if the method or member function is const or not, which is even uglier. And that's because of the syntax and how things stick together. And well, I've done enough macros in the last 35 years. it's a mess, implementing those macros. Using them can be, let's say, simplish, but if you fail to use it correctly, you get even messier error messages. Who is using macros regularly? Writing macros? Okay. Now, one means, what I recommend is if you have to write that fake stuff, just use plain code, because there you see what's happening. So the empty warehouse has inventory always returns false, and you write return false. You even get that generated if you generate that function from the tests. For GMock, you would write on-call warehouse has inventory with that arguments, Talisker 50, will by default return false. The point is you cannot use on-call, which would be the right thing. You have to write expect call, which is a little bit less stringent and doesn't give you an error message. To make on-call usable, you have to wrap the mock object again with the other class called niceMock to avoid having spurious output from actually a successful test case still generating you an output. And that's one of the big drawbacks of GMock. Trompe-l'oeil is a little bit nicer. So you can say allow call, the warehouse has inventory, and then it returns false. And note there macro magic happening. And I'm not sure, can you see that down? I hope so. So it says allow call, warehouse variable has inventory, return false. And this employs the magic that was created by the macros defining the class to actually do something that looks like what's happening there. Just consider that doesn't compile, how nice it is to debug that code or even figure out the compiler error messages if it fails to compile. It's lovely. What's that?
It's typically 10 to 15 lines. Exactly that source code line.
Okay. Now, that's the easy part, the faking. Even faking is simpler when you do it by hand, by coding it. Now, the next interesting part is the behavior verification, that actually that system under test operates in a specific sequence with the test fixture, with the other component. And that is a means of testing that's called white box testing, or when you don't have the other component yet and you want to make sure that you fulfill the protocol. And that leads to fragile tests and over-specification. Because when you later find out, oh, there's a simpler way to solve that problem of the system under test, you cannot change it easily because your 1,000 other test cases depending on that sequencing actually fail. So you have to change the tests. You cannot, with some of the testing frameworks, you cannot even refactor the API here. Because remember, it's hidden in these macro magics. I have not seen a refactoring tool that can actually refactor the code that employs the gtest macros to actually make useful refactorings from the API there. Not going to happen. And hard tests are bad tests. If your tests are overspecified and checking that some specific behavior internally happens, it will manifest that internal behavior even if it's ugly, wrong, or not very elegant. Just to give you some example, you can have sequences with a sequence object that you introduce in your test case with GMock and trompe-l'oeil, it's not much different. You provide that sequence object, and then it will actually kind of either magically by or with GMock, or at least explicitly with trompe-l'oeil, show you that something happened in that sequence as you specified it? Detlef?
That overspecification that is inherent to white box testing doesn't have to do anything with the mocking frameworks or whatever, but if you do white box testing, then of course you overspecify.
Detlef is saying, okay, if you do white box testing, you overspecify anyway, regardless what you're doing. Yes, but using a mocking framework like GMock actually makes it harder to refactor your code if you learn to make it different. And one reason is you have these interesting macros there, and there's no reasonable means to refactor what's these macros unless you know exactly what test framework you're using and then be able to refactor these macros automatically. And consider you have not only one of those test cases, but plenty. Detlef has a counter argument.
Are you actually claiming that if you don't use the mocking framework, then the refactoring can also refactor your test cases?
At least it's much easier, and we've done that. So because if you have plain code, the refactoring tool sees your code, and you see the code that's happening, so it's much easier to actually have that real refactoring, because the names are still the names that you have in a code base, and you can actually detect, even if you refactor manual, it's much easier to detect the places where an identifier is bound to a specific thing, like having all the callers around and grabbing them, even if you do refactoring manually.
Just want to ask, at the bottom there, the last bubble, are you trying to say that it makes an implicit check of the correct sequence when we go out of scope? Is that what you're saying?
At least that's how I adapted trompe-l'oeil in my unit testing framework. You can have that explicit checking in the sequence. So the question is, do I imply that, okay, at this curly braces, I have the implicit checking that the expectations given happening. With GMock, it happens like that, and with trompe-l'oeil, you can configure it like that. And that's what I did in that case. It's not inherent in trompe-l'oeil. I have to defend the author about that. It's not always like that, but it's kind of convenient with some issues.
The typical instrumentation rather is that you get an error report directly in the first call that violates the sequence.
Yes. But nevertheless, it happens when you finish, because the violation might just throw, or not. And my violations will throw. But that's details, it's not relevant. And the point is, I say, if you write mocks, program them yourself in the language that you use, because you end up with these interesting cheat sheet, at least for trompe-l'oeil, it fits on 2 pages, showing you how to program what your mock code should actually do. So it follows the tradition of the JMock thing, where you configure or specify in a separate language what actually should happen. Plus the matching part, how do you figure out, okay, what happened, and give it some leeway to one concrete sequence, giving some, okay, this is somehow like that, not exactly, but close enough. And it's another language you have to learn and master, where you don't have an IDE for, and where you don't have a debugger for. That's what I don't like about mocking frameworks. So how can you do differently? Kent Beck, also an old friend of mine, I remember telling me, oh, do the simplest thing that could possibly work if you don't know what to do. I did some digging, and it turned out it wasn't Kent, it was his buddy Ward, who always told Kent, do the simplest thing that could possibly work when you don't know what to do. And for those who might have forgotten, Ward Cunningham was the inventor of the very first wiki web. And he coined the term wiki web. Not Wikipedia, wiki web. The collaborative editing. And it's an example of do the simplest thing that could possibly work. And I'm not sure if anybody of you came across fit or fitness for writing acceptance tests, or let's say normal user provided tests. Is anybody using that? Never heard of fit or fitness? Learn about it. Ward invented fit, where you can write test specifications in HTML and glue it to your code and having them run automatically and color the HTML if the tests are okay on it. So managers can write tests using fit. And wiki users can write tests using fitness that was built by Bob Martin on top of the ideas of fit. So, Ward, great guy. Honor him. Buy him a beer or whatever he likes. So how is mocking, what's a simpler approach? When my former student, Michael Rueck, actually told me, I want to do some mocking, and I said, mocking is all BS. And yeah, how can we do it that it still works for C++ and is nicer? So we came up, what's the simplest thing? Okay, to actually know what happened, how my dependent other component, my replacement, my mock object was called, I need to do something. So what's the simplest thing to actually know what happened? Well, I build up a long string with the sequence what happens. And how do you do that interesting matching where we have that A4 sheet in Trompe where the matcher thinks is? Well, how do you match strings? We've got regex. Unfortunately, when we did that, GCC regex implementation was kind of non-existent but claimed to be there. Who lived that time? 10 years ago, something? So, but we had boost regex, so to the rescue. Nevertheless, so the simplest thing that we said, okay, I don't like macros. Well, there's this assert equal stuff and so where you cannot yet get rid of macros, but at least not these strange things of macros. And I want to create a string from that. And even though I hate globals, somehow we need to hook into that stuff there. So but the good thing, instead of writing code with VI or Emacs, we have the power of the IDE behind where you can generate structured code from the AST and transform the AST. So we are able to generate not only the theme code from the IDE, but also generate the code for the tracing that happens, generating our strings to figure out what happened. So what we do is actually we have a data structure called calls, which is a vector of call. And each call is more or less a string, or a little beefed up string where we put stuff together. And we actually notify the signatures. We can easily generate the code generating these signatures because we have the AST with the signature in our hand in the IDE, and so we can generate the string at editing time, and so you can actually sequence. But the generated code that generates these calls is regular C++ code. So if you don't like what it's automatically generated for you, you just can put your own strings there to trace what's going on and then match on that trace. So,
I have a question on
yeah.
that one. I was thinking about how you, in these expected mock warehouse and calls, I presume that this builds up a string concatenating all the matching.
Yeah.
Am I right? Yes. In this example, that is good. If I have a test that I want to order 2 whiskeys, say, then it's not important which is removed before the other. Doesn't this overspecify the sequencing?
If you have the problem that you have an overspecification, how do you do the matching? You don't do the matching like that. Because then you would actually use regular expressions or say, find in the vector did this happen? Find in the vector, did that happen? And then both have to happen, but you don't care about the sequence. So that's how you would do the matching then. There's no magic there. It's just plain code. You see what's happening. But you have to, let's say, be a little bit more proficient with C++.
What I wanted to say is that it's easy to overspecify, and it takes an effort to be general.
That's true. So if it's, let's say, even with the generated code, it's easy to overspecify. That's not safe. Doesn't save you from overspecification. And that's the general message as well. So don't overspecify. So to give you an example, again, you see this blue bar here. That's all code that's generated for you, and ugly, there is a little macro pulling in the infrastructure. That's for C++03 to get the infrastructure there. And oh, there's a static, yeah, but our tests run in single-threaded code. And this is the code that is generated for, okay, I push back that call object for the constructor. I push back the has inventory with the arguments that are, or the parameters providing the arguments that are given, and so on and so on. And in the end, I assert equality that my first call is actually happening the expected stuff. And because we compare now vectors of strings, we can get this nice output. And we see, oh, there was a mistake. The remove didn't happen from the warehouse, and that's missing. So that's how you actually end up with the calls. And if you have that situation that Björn asked for, oh, what if I want to remove both whiskeys and I don't have that sequencing requirement on the removal calls, then you end up with a little bit more work to do. And that's a good thing, because checking that if you remove two whiskeys, either order happens is a question, is it actually a case you need to check for, removing two whiskeys? But that's another test feedback, that if your test cases get ugly, maybe you're testing the wrong thing or your design is ugly. So in general, regardless of language, most mocking frameworks stem from the early designs and the limitation of that design space, Java 1998, 1999. Java has reflection, and building something where you don't have reflection like that requires magic. And we have celebrate magic tonight, but that's not the magic using macros that you want to have. And especially GoogleMock had a long phase in history where it only could do that magic with inheritance and virtual member functions with all the overheads. So your designs have to be object-oriented, even though that's only one corner of the design space using C++. And subclassing with that reflection is not what you want to do. And Java didn't have the lambdas then. And with lambdas, it's very easy to provide behavior. We didn't do that for Mocator, but even there you might just plug in a lambda to specify what's happening. So it's even more in place in your test case what you expect to get. And I'm not sure how trompe-l'oeil works with that. Do you have that?
I'm sorry, I was zoned out a bit. What was the question?
The question is, does trompe-l'oeil allow you to specify behavior by providing just a lambda?
Yes. Actually, in all these horrendous macros, you're allowed to write pretty much any code you like.
Okay, so you could write a lambda there.
Yes, the macros does create lambdas for you.
Okay, it employs lambdas to get that implementation stuff done, trompe-l'oeil, but it's not the first. It's the implementation approach, and that you wouldn't write the lambda. Yeah, it's not what you would get there. Now in C++, again, that design tends to follow what you got in Java, which you don't. It's not Java-ish design is not good C++. We don't yet have useful reflection. That might change in the next decade. There's hope it's earlier, but I'm not sure. But hope is there that and you have seen the talk by Herb Sutter about the reflection operator and generating stuff and iterating at compile time over existing stuff. If you have that, all the stuff we do in the IDE today can be done at compile time, which is also not that easy to debug. But possible. There are other frameworks like HippoMox, which do interesting thing, add runtime to your vtables to replace member functions with others, which is okay-ish, but better don't have an optimizing compiler getting rid of vtable entries. And he met that situation, good. So I'm not lying. And the ugly thing is about the DSLs to specify the expected behavior, not plain code. It's like, oh, I expect the turtle to the get y function of turtle to return 100, to return 200, and then repeatedly return 300, and that's not very nice to specify, especially to debug if it's wrong or if it fails. And that leads to fragile tests that are not easily refactorable, and to the over-specification of the test case and the test case bloat. Even though if the tests are sequential, if they are long, like any long function that doesn't fit on your 8025 screen, oh, that's 30 years ago, doesn't fit in 10 lines, it's something wrong. And even Bob Martin, who's often misunderstood by people, he says, too much mocking is bad. White box tests couple the test, the system under test, and the dependent other component. And it's very hard to refactor, not only for tools, but also manually, and you lose the design flexibility. And good design, not even only software, is postponing decisions as late as possible. So keeping the design space open, not overcommitting to a given design up front. And also what I observed is if you use test-driven development together with a mocking framework and non-existing either system under test and dependent other components, you foster stateful APIs. And I have a question. Who is loving stateful APIs? No one. And I hate them, and it's very hard. Like, oh, set wiggle, set waggle, and then wiggle the waggle. That's not very nice code. Especially, can I exchange the first two calls and it still wiggle the waggle? I don't know. And there has been a tendency to have very few parameters, which is good, but often misunderstood. Uncle Bob favors in his agile, what's the book called? Nice stars on it, Agile Software Development, I believe. He has a lot of niletic methods in his Java code, but he says avoid temporal coupling. So even if you don't provide an explicit additional parameter to the object that is implicit, you shouldn't have them that you have these temporal coupling, these stateful APIs. What's the problem there? Why is it so hard to refactor? First, the DSL, again our turtle example, turtle graphics, move around, do something. It mixes the behavior, oh, return 100, return 200, return 300, with the expectation, oh, it's in that sequence, first 100, then 200, and 300. If it's not called that way, something bad happened. So we have that very ugly DSL, very specific setup code while configuring our testable, our mock object. And then we have that implicit or explicit verification in the end, checking that these calls have been made in a given way, either with the matcher infrastructure or implicitly by the sequence of what we provided. And that What it does is actually it glues our test cases with the API of the system under test, because if you want to rename or change the interface of one of the member functions or group them differently functionality, oh shit, we have 100 tests for that class and we have to change all of them manually because my refactoring tool doesn't understand the macros there. And on the other hand, it also overspecifies the interaction between, so if the dependent other component is not yet existing, you manifest its interface. And the worst thing that can happen when you write software is making it rigid before you know what you're actually doing. And making it rigid, even if you know after you're doing, you often know better how to change it afterwards when you've done it once or twice. You get new ideas, and having that super glued is not nice. Just to remind you, put your super glue on your hand and stick it somewhere on the wall. See how nice that feels. That's what happens to your tests and your code. And I know what I'm talking about. It happened to me a couple of times. You use a little bit of skin usually. And that's not very nice. Now, stateful APIs, we all love them. Oh no, we hate them. Why is it bad? Well, a typical thing is I acquire a resource, I use it over time, and then I release it. That's a typical stateful API, and that's a good stateful API. Because in C++, we have the mechanism to actually make that work without the need to think about. Why? Well, we can acquire a resource constructing an object. The constructor will acquire the resource. Then we use the object, and when we forget the object, the destructor will actually release the resource, and we're done. Magic happens, and that's the magic of C++. Celebrate that tonight. If you can't have that RAII, resource acquisition is initialization. It's a cornerstone of C++. If you can't have that, like in Java, you can forget to release it. Or in C++, in very bad old C++, we have two-phase initialization that often happens in situations, oh, we are not allowed to throw exceptions, so we construct something, and then you initialize it, and initialize tells you if it was okay or not. Bad, bad, bad. If you have a class, define its invariant and guarantee its invariant in the constructor, and crash or do something about it when the constructor cannot guarantee the invariant. Two-phase init is whatever that emoji means there for you. And there are other stateful APIs that are really hard to test and easily to misuse or not work correctly. One big example is sockets. Who has programmed sockets in his life or her life? Who got it wrong at least once? And that's a classic. The original Unix guys, so Kernighan, Ritchie, and their friends, they got it right. They had open, establishing a resource, directly usable, read, write, and then close. Done. You could forget the close, but when the process was done, it was closed implicitly. So we had a single-step initialization, the operation, and the finish. And then somehow in Berkeley, maybe it's the problem of the West Coast const, had this interesting idea, oh, I use one abstraction socket, and I use it for many things, but because I use it for many things, I'm not able to initialize it completely by calling socket. No, that's just establishes a handle, and then I have infrastructure to wriggle around to do something useful for it. And if I have a server socket, I have to bind it to an address so I can actually connect to it. I have to establish the serverish thing with the listen call. Who knows what the arguments to listens do? Are they actually Say it?
The argument to listen. I think most things ignore it.
The argument to listen is most of the time ignored, but you don't know, and it has an official property, but it's ignored by the kernels because they know better than you. But when it was conceived, the people who invented that interface didn't know exactly what to do yet because there was no experience in using sockets, so they didn't know what the queue lengths of the accept queue lengths should be, so they provided a parameter that nobody actually uses anymore. And you have to close twice. You have to close the accept socket and the operational socket in the end, so it's ugly. The problem that I have seen is that languages who wrap that C API that is very ugly still provide these initialization steps, at least some of them. If I remember correctly, Perl sockets had that, and I believe even Ruby or Python had that for some time. Bad, bad, bad. Wrap, if you have these multi-step initializations in some other language or in some other library, wrap them so it's usable as a single step initialization. Other stateful APIs. Who's used Turtle graphics in his or her life? Cairo, something similar. It occurs. It's easy to teach for beginners. Oh, you move around the turtle and it's somewhere and you have stuff that you can do. But it leads to stuff, oh, if it doesn't work like I intended to do, what happens? You wiggle around with the sequence of the calls you're doing. And that leads to situations that the pragmatic programmers call programming by coincidence. Oh, it doesn't work. In that example, there was that other call. Maybe fiddle it in somewhere in the middle and it might work. And it might even work, but you don't know why. And having code where you don't know why it works, it's very, very bad. I still get students who do that, and that's where I take their neck and shake them until they get it, virtually. That's cargo cult programming is something like that. Or Stack Overflow, copy-paste programming is also something like that. What's that? Block-driven development is also in that, block with G, yeah. Well, if I need sequencing, take the sequencing, oh, I want to have initialization, step 1, step 2, step 3. Nest the calls to get the final thing. Like, oh, I want to have the last thing, but I first have to do first, then second, then third, then wrap the objects correspondingly or the initialization functions correspondingly. You have the guaranteed sequencing, at least in that way. Be aware, if you have commas somewhere, sequencing is no longer guaranteed in C++. But nevertheless, there is a means to spell that out and provide the API correspondingly. Get the abstractions right. Don't put everything under one handle type. So stateful APIs lead to programming by coincidence, and mocking frameworks tend to foster stateful APIs if they are applied to dependent other components and system under test that both don't exist yet. Sequence matchers. If you have a stateful API that's given to you, like socket, then you might want to have actually these sequence checkers to make sure that your component calls socket first, bind and listen afterwards, and then accept. And not socket, accept, and then bind. But that's a rare case. And that's an API you cannot change. We don't have a time machine to get that head wiggling with the BSD folks in Berkeley. So if the dependent other component cannot or will not be refactored, then it's okay, and it has a stateful API, then it's okay to use mocking framework and sequence matches. And if you cannot wrap the dependent other component with a wrapper that is easier to use, acquire, use, release, Or if you're building that wrapper, then you might actually want to have that mocking to actually make sure that your wrapper is doing the right thing and write tests for the wrapper. But those should be rare. And there might be other reasons that I don't know about yet, but that's more or less, you're building wrappers and you have an API that will never change. That's where you actually should use these sequence matchers and mocking frameworks.
Another example is hardware access.
What's that?
Another example is hardware access.
But hardware access is another example, but that's, again, you have a given interface and you cannot change it, so you write a wrapper around a hardware access, which is similar things. Oh, you have to set that bit in that register at that address, and then that other bit, and then some magic happens. That's another where you actually want to have, where you need to know that the bits are set in the right sequence by your code base. But again, things like that you should wrap as soon as possible and not leak up to the abstraction hierarchy that you're building. So if you need to test legacy code, first, get Michael Feather's book. Second, watch the videos how we do it, and then consider for yourself what you're doing with that. And take the power of C++ and the IDEs, regardless of which one, to actually get the simplest solution that works and that's still manageable and readable and might survive Google's, how do you say, disemboweling by the, if they are too big and too powerful, or nobody is actually buying advertisements anymore, then they will fail. But nevertheless, or they just abandon their stuff, which they have in the past. If they don't sell ads from that and don't use it internally heavily, it's easy for them to abandon something. Be aware of the big things. And sometimes DIY is okay-ish, especially writing a mock class. If you have a non-changeable stateful API that you have to program against, like a piece of hardware, like something like socket, it's okay to use mocking to check the sequencing, but do it yourself, or maybe use a mocking framework like Trompe. Beware of the dangers for new code design if something new are doing it, especially because you might end up prematurely designing a stateful API that you end up having to use all over the place. Do not mock unwritten code with a mocking framework. That's where you get the super clue automatically put on your hand from the mocking framework and stuck to the table. And then you have to get away with that. And keep it simple applies to test automation as well. Write tests. Those who are not writing tests yet, start now, tomorrow, maybe next week when you don't have a computer here, and automate everything. Thank you.